Chapter 11, sections 5 through 7 all relate to each other, and they're pretty short, so we are just going to combine them in this one video. The way that we determine where the lattice points are, how we have a face-centered cubic or a body-centered cubic or any one of those other various types of unit cells, was and is determined by X-ray diffraction. Now this isn't exactly to scale because the crystal here, at least when I was doing this in the 90s, has to be 1/10 of 1 millimeter. In all three dimensions. And so that's not a very big crystal, but when you're trying to crystallize things like proteins or the AIDS virus or some of the massive liquid crystals that I was dealing with when I was in grad school, getting 1/10 of a millimeter on all three sides was quite a challenge. I think that with today's technology, you can have even slightly smaller than that, but you still need to have, at the atomic level, definitely an extended network of well-arranged atoms, ions, or molecules, and that can be a challenge to crystallize really, really large things. So the X-rays that are coming out of this X-ray generator are on the order, the wavelength is on the order of the spacing between particles, molecules, atoms, or ions. And so using the Bragg equation, which we are not going to do, you can, from that spot diffraction pattern that results, determine where individual atoms are in the structure. There used to be a lot of art to that science. With computing power, the amount of user input has definitely decreased. But for example, the guy that did this at Indiana University when I was in grad school had been doing it for quite some time, and not rather than just paying him, he has to have his name on every publication where he did solve the X-ray structure, as it's called, and the guy ended up with thousands and thousands of publications because he wasn't in the lab actually mixing the stuff together, but he was the one, in the early days of computing power in the 60s and 70s, figuring out these structures, figuring out using the Bragg equation to determine pretty much by hand where the atoms were. So that's enough on X-ray structures. 11.6 has to do with types of crystals, but types of ionic crystals. So as you might expect, an ionic crystal, the lattice points are occupied by cations and anions. So sodium chloride is a nice example of this, although I don't have the picture for that. It's the one that you've seen over and over and over and over and over with NAs and CLs at alternating lattice points of a simple cubic structure. What holds the ions together is electrostatic attraction, plus-minus attraction. They are hard, brittle, and have high melting points because, think about it, all you have to do is shift that structure by 1 ion distance, and then you have, instead of plus-minus attraction, you have plus-plus and minus-minus repulsion, and so the cube shatters apart. They don't conduct heat and electricity well because in the solid state there are still these gaps that are huge compared to the size of an electron, and they can't hop across it. So you have opposites attracting the electrostatic attraction between cation and anion, but you do not have conduction of electrons through the structure. So this is a body-centered cubic structure, this is a face-centered cubic structure, and so on and so forth. You don't need to know the types of structures, but just understand that the lattice points and the face points on some of these and the vertices in these are occupied by cations and anions. That's the bottom line. What is an ionic crystal? Lattice points are occupied by cations and anions. We're not going to do this question because it relies on that information that we skipped about how many unit cells is this one in 8, how many unit cells is this one in 4, how many unit cells is this one in 2. And so you can calculate the number of Na pluses and Cl minuses that are in this, and therefore calculate the density. But we're not doing it. Superconductors, there's an interesting chemistry in action discussion of this over 2 pages. Superconductors may be the way of the future, maybe not. At first, things superconducted lost all resistance to electrical flow at around 4 Kelvin, which is liquid helium temperatures, which is very expensive. Now we've gotten them up to 95 Kelvin and a little bit higher even, which is above the temperature of liquid nitrogen, 75 Kelvin, which is much, much, much cheaper. We want room temperature superconductors. That would be awesome. About 40% of the power that's generated at the power station is lost in transmission, meaning the electricity that you use at your house and you're paying for it at your house, you also have to pay for the extra, right, that is lost because the power company is producing it, but nobody's getting to use it because 40% of what they produce is lost going through the power lines due to resistance of the power lines. If we could have superconducting power lines, that'd be awesome. Then our electricity gets to our houses without resistance. We have an immediate 40% gain in power plant production because we're not losing it. And the use of superconductors that you've probably most often seen is magnetically levitated trains for transportation. Novel, but certainly not energy efficient at present. Covalent crystals, you might not be too surprised, have lattice points that are occupied by atoms. Molecular crystals will be on the next one. They're held together by covalent bonds. They are hard, have high melting points. The great example of this is diamond. All sp3 hybridized carbon as opposed to graphite, all sp2 hybridized carbon in sheets. It's very hard to break these apart because you can't shift it by an atom's distance and get repulsion. It's all covalent bonds, and so that's why diamond is incredibly, incredibly hard. Graphite sheets slide nice and easily because of the effectively sheets of electrons between the sheets of nuclei. So they slide nicely, but breaking apart the sheet itself is very, very, very challenging. Single layer graphite is known as graphene. It was just discovered by accident a couple years ago. And using graphite, graphene, carbon type sheets like this to make Kevlar and various other materials that are incredibly strong to penetration, yet and stretching, but don't have much weight to them because of the carbon sheets. Molecular crystals, not surprisingly, lattice points occupied by molecules, held together by intermolecular forces. So these guys are going to be soft. They're going to have low melting points as opposed to the other ones that were held together by the intramolecular forces, in effect, having a giant covalent crystal or a salt crystal where you had the electrostatic interaction. They don't conduct heat or electricity well, again, because of the gigantically large gaps between the particles. Notice water has its solid floating and benzene has its solid sinking, as is more typical for compounds. Both cases, the solid would be a molecular crystal. You know water doesn't conduct, even though it's a polar molecule, without the presence of ions. Ditto for benzene. It's a nonpolar molecule. It's definitely not going to conduct. Metallic crystals, we're not going to really spend much time on at all, but the lattice points are occupied by metal atoms. I think of metallic solids as a peanut butter and jelly sandwich, where you got your bread is the nuclei and your peanut butter jelly is smeared across the top. That is your mobile sea of electrons, is how it's usually referred to. You don't know which electrons belong with which nucleus, and that is why metals conduct so well. You pop an electron over here, one can pop out over there because it doesn't belong to any one nucleus. It's just kind of smeared across the top. The rest of this area we're going to kind of just jump over. We don't really need that much, but table 11.4 is a great summary. I'll leave it here for a second so you can pause the recording if you would like to look back over it. But 11.4 is definitely where you want to put your energy for what you're looking at for section 11.6. 11.7 is a single slide on amorphous solids which lack a regular arrangement. Glasses are an example of this. They're cooled to a solid state without crystallizing. So here you have your regular arrangement of a sand crystal on the left, but then non-crystalline glass is definitely a less regular arrangement of the SiO2 extended network. Okay, it's not a regular arrangement, and that's why it's optically transparent. Interestingly, there was a talk given by a professor here at Queensborough a couple of years ago how drugs actually work better biologically. They're more bioavailable in the non-crystalline and amorphous state rather than a crystalline state. To me, this was very odd because in my lab in grad school, we were all about trying to grow crystals so we could determine the structure. In his lab, it's all about how can we prevent these compounds from crystallizing because they're less bioavailable. Fascinating talk. Fascinating talk. That's the end of section 11.5 through 11.7. We will do section 11.8, which is a bit longer, on the next video.